Welcome back to the Nutrient Management Seminar Series for our final presentation. Today, I have the pleasure of presenting on the Phosphorus Filter Project, which is a joint project between East Raymond Colony, the County of Warner, Alberta Agriculture and Forestry, and of course, the Canadian Agricultural Partnership. My name is Brad Calder, and I'm an Agricultural Extension Specialist with the County of Warner Ag Service Board, where I help producers and the public with agribusiness sustainability, agri-environmental concerns, and invasive species. Primarily, my work has been on the Phosphorus Filter Project, which is one project of a larger initiative near the Milk River Ridge Reservoir. The Milk River Ridge Reservoir Water Quality Stewardship Initiative is a multifaceted program to mitigate agricultural runoff and its nutrient contributions to the watershed through boundary fencing, planting of native species, and water quality sampling of the reservoir. I wanted to thank our organizing committee and the County of Warner for the opportunity to present at this series and of course to host the series. It's a great opportunity and I really appreciate it. Welcome to the presentation on the phosphorus filter, mitigation options for nutrient contributions from agricultural runoff. My name is Brad Calder and I work with the County of Warner as an Ag Extension Specialist. Before I begin, I'd like to thank the Canadian Agricultural Partnership for providing funding for this project. I'd also like to thank our project partners, the Huddersfield and Brethren and Alberta Agriculture and Forestry. Thank you very much for your support. The project would not be possible without it. Throughout the presentation today, I'll be discussing agricultural runoff, which typically contains increased concentrations of nutrients such as nitrogen and phosphorus. These nutrients may contribute to algal and cyanobacteria blooms, which degrade water quality through advanced eutrophication of a water body, hypoxia, and cyanotoxin release. Now these pollutants flow downstream, affecting all downstream watersheds. A watershed that has been negatively affected by nutrient contributions includes the Gulf of Mexico Dead Zone, which is an area of hypoxic waters at the mouth of the Mississippi River. Its area varies in size, but it can cover up to 6,000 to 7,000 square miles. It occurs between the inner and mid-continental shelf in the northern Gulf of Mexico, beginning at the Mississippi River Delta and extending westward into the upper Texas coast. It's the largest dead zone ever recorded, and I know you're all asking, how does this relate to me? I'm a farmer, or I live in the city in southern Alberta. Why is this relevant? Oh, please stay tuned. Getting closer to Canada, Lake Erie is another example of a watershed that has been negatively affected by nutrient contributions. In Lake Erie, in 2014, toxic algal blooms resulted in fouled water that hundreds of thousands of people rely on for drinking, cooking, and bathing, forcing hundreds of thousands of people to rely on bottled water. Blue-green algae, or cyanobacteria, choke up huge portions of the lake and have re-emerged as an annual summertime problem after nearly disappearing for more than a decade. And although the size of the bloom varies from year to year, in 2014 the bloom was nothing compared to the 2011 record breaker that took over a whopping 5,000 square kilometers of the lake. There is clearly a trend towards larger blooms. And I know what you're thinking, sure that's in Canada, but that's a long ways from my farm or community in southern Alberta. How is that relevant to me? Getting closer to home, southern Alberta is no stranger to cyanobacteria blooms. Blue-green algae advisories are typically issued in late August to late September, when surface water temperatures are elevated. In 2018, an advisory was issued for Chin Reservoir. This past summer, an advisory was issued for the Milk River Ridge Reservoir. This is a photograph from the shoreline of Milk River Ridge Reservoir in Ridge Park from the boat docks. And this is but one example of many within Alberta, as many of the reservoirs in southern Alberta are eutrophic systems. These are rich in dissolved nutrients that stimulate the growth of aquatic plant life. And decomposition of that plant life results in the depletion of dissolved oxygen, resulting in hypoxia. Some of the reservoirs can at warmer times of the year experience blooms of blue-green algae, also known as cyanobacteria. The cyanobacteria is a naturally occurring bacterium that is found within many water bodies throughout the world. During periods of increased temperatures, large populations can develop, which release a toxin, which is a cyanotoxin microcystin, that can result in death by respiratory system failure or liver cirrhosis and failure. While this bloom dissipated days later, it is important that if you notice blooms of this bacteria within water bodies and water sources such as springs and water troughs, that you prevent animals and livestock from entering or consuming the water and clean out that water source. It comes at no surprise that agriculture depends on fresh water. It's the largest use of fresh water in the world. In 2000, agriculture accounted for 67% of the world's total freshwater withdrawal and 86% of its consumption. This water is of course returned via the hydrological cycle, however, with added nutrients, pesticides, manure, and other pollutants, which impact water sources. This increases water treatment cost, negatively affects ecotourism, and negatively affects the aquatic ecosystems, which affect terrestrial ecosystems as well, resulting in declines in species populations, affecting biodiversity, and many other effects. There's many different beneficial management practices that can be implemented to control nutrient contributions to downstream watersheds. These include conservation tillage, crop nutrient management, pest management, conservation buffers, irrigation management, grazing management, animal feeding operations management, and erosion and sediment controls. I know what you're thinking, I'm just a farmer or a rancher, or I own a golf course in Alberta. I don't have a lot of money to invest in new technology. And why should I spend a bunch of money to solve problems millions of kilometers away from me? What can I do on a farm level to mitigate problems more closer to me? Throughout this presentation today, I'll be discussing the phosphorus filter, which fits loosely into the animal feeding operations management and erosion and sediment control areas. Phosphorus is an essential nutrient for plant and animal growth because it's a key element in many physiological and biochemical processes. Alberta soils are generally low in phosphorus for optimum crop production, less than 60 parts per million crop available phosphorus in the top 15 centimeters of that soil profile. Successful crop production often requires the addition of phosphorus in the form of chemical fertilizer or manure to the soil. Phosphorus is also added to livestock diets to ensure optimal growth, and much of that ingested phosphorus is excreted in the urine and feces. As part of the natural and essential nutrient cycling, phosphorus adheres tightly to the soil profile, so it is commonly transported by erosion from the landscape. Runoff from agricultural systems and from land development, pollution from septic systems and sewers, manure and sewage sludge spreading, as well as other human-related activities. These may increase the movement of phosphorus containing inorganic and organic substances into aquatic systems. Phosphorus occurs in many chemical forms in soil and water. However, it is generally not very mobile in the soil, unlike some nutrients such as nitrogen. Also, phosphorus does not have a gaseous form that forms through the atmosphere, like other essential nutrients. Phosphorus is readily absorbed by soil particles and generally does not leach through the soil profile unless soil phosphorus levels are excessive. And then it can migrate downward with water movement. Generally, overapplied phosphorus tends to accumulate and stay near the soil surface, and this can increase the risk of phosphorus loss through soil erosion and surface runoff. In soil, not all phosphorus is the same. It can be either organic or inorganic molecules. In addition, the molecules that contain phosphorus will change as the soil through nutrient cycling. Phosphorus inputs into the soil for agricultural purposes are primarily from the application of chemical fertilizer and organic sources, such as manure. Soil phosphorus is categorized into three types: soluble phosphorus, labile phosphorus, and stable phosphorus. Throughout the presentation today, I'll be discussing the soluble phosphorus phase. Soluble phosphorus is a very small part of the total soil phosphorus, but it's a fraction taken up by plants. It can enter the surface water bodies and is biologically available and can rapidly stimulate aquatic growth. Phosphorus moves from the landscape attached to the soil particles carried by wind or water and in dissolved forms carried by surface water runoff. Particulate phosphorus refers to all forms of phosphorus stored by soil particles and organic matter. Dissolved phosphorus, or DP, refers to the form of phosphorus dissolved in the surface runoff. Once mobile, phosphorus can be redeposited elsewhere on the landscape or be carried to surface water and potentially degrading water quality. Surface water runoff can transport nutrients such as phosphorus and nitrogen from livestock manure and fertilized agricultural fields into freshwater bodies. Oklahoma State University researchers have been developing phosphorus filters to effectively remove dissolved phosphorus from surface water runoff. In Alberta, most of the phosphorus is in the dissolved form, which is readily available to algae and aquatic plants, which can result in algal blooms, excessive plant growth, which both cause deterioration of water quality. The phosphorus filters are designed to use industrial byproducts such as fly ash, steel slag, red shale, and other synthetic materials such as biomass. These can be used as a filter media to capture and hold the dissolved phosphorus and thus preventing it from moving into the water body. Within the filter structure, the runoff wastewater is introduced to the filter media through perforated PVC pipes. The water flows down through the media, and the PSM binds the dissolved phosphorus, thus reducing the concentration in the water. The water flows out of the perforated PVC pipe and out of the filter system. It is important to have the filter system drain into an area that is resistant to soil erosion, such as a vegetated buffer. The material on the left-hand side of the screen is the iron slag that was used in the 2020 phosphorus filter. The slag is coarse and rock-like, varies greatly in size. This sample contains more fine material than the material used in the filter. The slag is quite dense, and the variable abrasive surface of the material prevents it from flowing easily. The material right on the right-hand side is the biomass material that was used in the Tributary 4 phosphorus filter. This material is granular and is comprised of some form of organic granule with fine pieces of iron. There are many different filter structures that are generally specialized to meet the project objectives and site conditions. The filters are built to match the filter media that is used. And the filter must also be constructed to meet the runoff velocity and volumes for an increased precipitation event. Some of the possible filter structures include surface confined bed filters, blind inlets, ditch filters, and specialized designs such as tile drainage filter boxes, submerged cages, and membranous filter systems. In 2017, Alberta Agriculture and Forestry staff, in partnership with the County of Warner, are verifying the effectiveness of the phosphorus filter technology in Alberta through the installation of a phosphorus filter in a known nutrient-rich runoff environment. The primary purpose of this is to determine if the phosphorus filter is effective under Alberta's environmental conditions. This site will become a demonstration site for producers and producer groups in the future to determine if the phosphorus filter technology is a cost-effective management option that can mitigate phosphorus loss and be a beneficial management practice option for landscape and production systems in Alberta. Water sampling to date indicates phosphorus removal is approximately 95%, and the phosphorus filter is still being monitored for its filter effectiveness. It's the first filter in Canada. It's located on Tributary 4, just north of Highway 506, and it is a $70,000 project. Project partners include the County of Warner, the OK Colony, Oklahoma State University, and of course, as mentioned, Alberta Agriculture, Environmental Stewardship Division, and Irrigation and Farm Water Division. This project includes evaluating the effectiveness of phosphorus filter technology in Alberta and includes testing it out on a large watershed and water volumes. The purpose of this is to determine if filter material will freeze and perform in freeze-thaw effects. Water samples have continued to be taken. However, the project has since been decommissioned. This is a tributary for phosphorus filter after it was installed. This is the tributary for phosphorus filter after it was installed. As you can see within the filter structure, there's a gray material. This is a gravel layer that is overlying the Biomax filter material shown earlier in the presentation. The Biomax material is a more expensive filter material made in Southern California. As mentioned, there's many other filters materials that can be used, such as fly ash, steel slag, and red shale. To provide you with an aerial view of the project site, this shot was collected using a drone that is facing to the southwest. Tributary 4 flows from OK Colony to the northeast. The site dam was constructed to serve as a water storage to supply water that flows through the filter structure. The instrumentation shed, as shown, includes a weather station and ISCO water samplers that were used to collect water samples from the filter structure. The flume was used to measure the water flow from the reservoir, and the project area was fenced, and an off-site watering station was installed to provide water to livestock that are fenced in the parcel following harvest. The lessons learned at the OK Colony Tributary 4 phosphorus filter were implemented at a second site in 2020. The purpose of this site is primarily to mitigate agricultural runoff contributions to downstream irrigation infrastructure. The agricultural runoff can contribute nutrients and fecal coliforms that degrade water quality downstream. These nutrients can also contribute to cyanobacteria blooms and excessive algal growths. To improve water quality, the County of Warner Ag Service Board partnered with Alberta Agriculture and Forestry and the East Raymond Colony to conduct a larger scale research project to install and evaluate a multi-stage phosphorus filter and bioreactor to remediate agricultural runoff from a confined cattle feeding operation. The goal of this project is to reduce the nutrient contributions to surface water in order to improve water quality. Improving water quality within the County of Warner can decrease costs in water treatment and improve water availability to livestock, agricultural projects, and to our communities. The lessons learned in this project can be applied to other agricultural businesses, communities, and recreational facilities, such as golf courses. In May of 2019, a drone survey was conducted of the project site by Alberta Agriculture and Forestry. This was primarily done to evaluate the changes in topography across the site and to obtain the elevations. In May of 2020, the project site was marked out with the filter site location and the location of each of the filter cells. This was conducted by Alberta Agriculture and Forestry and the County of Warner. On June 15th of 2020, the project construction began with the excavation of each of the filter cells, as you can see in these photographs. The phosphorus filter includes a wooden channel that diverts runoff downslope into the 3 excavations. The wooden channel was constructed to provide laminar flow into the filter structure and also to measure the water velocity flowing into the filter. The first excavation is filled with 3 different sizes of gravel, which functions as a mechanical filter, removing the coarse organics and manure from that runoff. Water flows into a biofilter, which is a lined excavation filled with flax straw. The flax straw provides a carbon source and a home to denitrifying bacteria, which consume the nitrogen from the runoff. This bacteria will decrease the nitrogen concentration in the runoff. And as the filter fills with water, it will flow into a third excavation that is filled with metal slag. The flax straw selected for the phosphorus filter was chosen because of its availability and for the physical properties of the straw. Flax is generally resistant to microbial decomposition, however it does not last as long as wood chips. There's many different bioreactor materials you can select from, such as cereal straw from wheat, durum, or barley, wood chips, coconut fiber, and hemp straw. These options all vary in their physical properties. However, it makes sense to use a filter type that is local, inexpensive, and meets your project needs. Alberta Agriculture and Forestry has done quite a bit of work in comparing the various bioreactor materials available in the province. The primary purpose of the filter material is to provide a carbon source for denitrifying heterotrophic bacteria, which use the cellular structure of the filter material as an energy source. Once introduced into the aquatic environment, nitrogen can exist in several forms, such as dissolved nitrogen gas, N2, ammonia, NH3 and NH4 positive, nitrite, NO2 negative, nitrate, NO3 negative, and organic nitrogen as protein matter, or in dissolved or particulate phases. Water was introduced into the filter structure bioreactor following construction. With that water, a population of bacteria, protists, and fungi were introduced. Within the filter structure, bacteria got right to work, consuming the available nutrients and using that as an energy source for growth and reproduction. Bacteria such as Nitrosomos, Nitrosococcus, Nitrospirna began a biological process of nitrification within the filter. The process involves the conversion of ammonia to nitrite and nitrite to nitrate. Second step of the nitrification process, nitro-oxidizing bacteria oxidize nitrite to nitrate. Nitrobacter is the genus most frequently associated with this second step, although other genera, such as Nitrospina, Nitrococcus, and Nitrospira, can also autotrophically oxidize nitrite. Denitrification is the process by which nitrates are reduced to gaseous nitrogen by facultative anaerobes. These facultative anaerobes flourish in anoxic conditions as they use nitrate in place of the oxygen as an electron acceptor when they are metabolizing carbon substrates. The biological process of denitrification involves reduction of nitrate, nitrogen, to nitrogen gas, but may also include nitrous oxide, N2O, or nitric oxide, NO. Gaseous nitrogen is not readily available for biological growth. Thus, denitrification converts nitrogen to a harmless form that has no significant effect on the environment. The principal biochemical pathways, however, are not anaerobic, but are merely minor modifications of aerobic biochemical pathways. Denitrification is a two-step process in which the first step is the conversion of nitrate into nitrite. The second step involves nitrite through two intermediates to nitrogen gas. Denitrification is considered a heterotrophic process conducted by microorganisms that require reduced organic substrate for energy and cell synthesis. The denitrifying heterotrophic bacteria convert the available nitrates from the agricultural runoff into free atmospheric nitrogen and use the energy from that for growth and reproduction. There are a number of different bacterial species that can perform this biological process, and a carbon source must be available for the process to occur. The flax filter material would serve that purpose. Something to note is that denitrifying bacteria are generally more difficult to cultivate than nitrifying bacteria, and you have to be careful not to flush them out of the system. Third excavation is filled with metal slag, and that metal slag is about 50% calcium oxide, 40% iron oxide, and 10% silicon oxide, with trace amounts of magnesium, manganese, and sulfur. The metal slag will bind with dissolved phosphorus and decrease the phosphorus concentration in the runoff. The steel slag, a waste byproduct of steel refining, was purchased in Edmonton and transported down to the County of Warner Ag Service Board shop. From here, it was transported out to the site in a trailer and loaded into the phosphorus filter. As you can see from the video, it's a granular material, and there was a certain degree of moisture in it as there was a rain event a few days prior to transport in Edmonton. This video shows a landscape shot of the project site. You can see the wooden channel and cobble overflow channel, which would be used to divert increased runoff amounts should we encounter a drastic precipitation event. The PVC pipe is shown near the channel will divert water from the wooden channel into the filter. Within that channel, 2 weirs are present, as shown. The water flows over those weirs and into the pipe, which flows into the gravel filter. Connecting the gravel filter to the bioreactor is a PVC pipe. As water fills the gravel filter, it flows into the bioreactor. The large black object shown is a flax bale covered in geotechnical fabric that is used to stabilize the boundary between the gravel and bioreactor, which was weakened during the rain events after the excavation. The bioreactor was filled with flax and covered with a geotechnical fabric and topsoil overburden to insulate the filter. As expected, there was settling of the filter material. The bioreactor has averaged 4 degrees Celsius over the winter, even on the night of February 12th, in which the atmospheric temperature was minus 35 degrees Celsius. The flax will degrade over time and may require recharge through the addition of more flax straw. The topsoil was seeded to a grass mix and covered with, as were the berms used to collect runoff, as shown. The instrument shed houses the wiring for the flow sensors and temperature probes. It also houses 2 auto sensors. The solar panels provide current to passively recharge 2 12-volt batteries within the shed, which power the ISCO water samplers. Now you may think that the exposed wires on the site are disorganized, but in reality, if you place these within steel conduit, mice tend to chew the wires. The vertical PVC pipes sticking out of the filter structures provide an access point for the temperature sensors and permit the direct sampling of water from the filters. These ports will also allow the introduction of water to flush out the filter if needed. The site must be fenced to prevent cattle damage, and the phosphorus filter, which is visible, has a PVC distribution network, which allows the water which flows into the filter to be evenly applied to the slag material to increase absorption of the dissolved phosphorus. From the phosphorus filter, the water flows downslope through a pipe and away from the filter. This year within the county was unusually wet. In the spring and early summer, we received increased precipitation. Most notably was May 21st, in which 15 millimeters fell, followed by an additional 43 millimeters. This saturated the confined feeding pens, and there was runoff downslope through the filter project area and off-site to the east. This flashy precipitation event really demonstrated the need for a mitigation option, such as a filter at the site. Precipitation caused delays throughout the construction process, as shortly after beginning to excavate, on June 15th, consistent rains from June 16th to July 1st routinely saturated the site and caused subsistence issues within the excavations. Which brings us to the primary reason in which we installed this phosphorus filter in southern Alberta: snowfall and sub-zero temperatures. The primary reason this was installed was to evaluate its performance with the freeze-thaw cycles to see if this is a viable means of removing dissolved phosphorus from agricultural runoff in southern Alberta. Throughout this project, I had the pleasure of working with Ken Jansen, a technological expert who worked extremely hard to make the project a success. He set up the sensors at the site to be accessible through an iPhone app called LoggerLink, as shown in the figures. Through this app, a person can access the sensors at the site to obtain a real-time measurement of the site conditions, including the temperatures of the panel, the filter cells, air temperature, relative humidity, and a water velocity measurement of the flow sensors. As well, you can obtain the status of the ISCO samplers. The iPhone app connects to a number of temperature sensors which extend down into each of the filter cells. It also connects to a pressure probe OTT PLS pressure transducer. This device is used for precisely measuring the water level of ground and surface waters through use of hydrostatic pressure of the water column above a relative pressure measuring cell. A pressure compensation capillary in the pressure probe cable gives the measuring cell the current ambient air pressure as a reference. This device was mounted within the entrance of the wooden channel. This pressure transducer will detect water flowing into the channel and send a signal to the app. This is an enclosed sensor that vents through an external interface that is located in the enclosed steel box. The device is manufactured by Campbell Scientific. The device used for measuring the flow of water out of the phosphorus filter is the Grayline Instruments Area Velocity Flow Meter Model AV-FM 5.0. The device uses a submerged ultrasonic sensor to continuously measure both velocity and level in the pipe. The sensor resists fouling corrosion. And the flow meter can be configured with the standard submerged velocity level sensor or with the submerged velocity plus a separate non-contacting ultrasonic level sensor. The QZ02L sensor was used in our circumstance. For the producers in the audience that are looking to implement a phosphorus management strategy, the Alberta Phosphorus Management Tool is a risk assessment tool designed to help producers make livestock and nutrient management decisions that will minimize environmental risk associated with the loss of phosphorus and to maximize the benefits of manure and fertilizer nutrients. It also serves as an educational tool to explain how management practices and landscape features impact phosphorus loss, and which beneficial management practices can be used to mitigate that loss. This risk assessment tool helps farmers plan their on-farm phosphorus management. It's a Windows-based program developed by the Government of Alberta as part of the Alberta Phosphorus Watershed Project. I'm sure throughout this presentation you've noticed Chad Penn's name a few times. His team at the USDA has developed a P-TRAP, or Phosphorus Transport Reduction app, which allows a user to design different types of phosphorus removal structures based on site conditions, phosphorus absorbing material characteristics, and structure parameters. The P-TRAP software allows users to explore different designs to meet performance goals for P removal amounts and material lifetime. It has a database of P absorbing material characteristics based on previously completed laboratory experiments. I encourage you to check out the software, it's quite interesting. In closing, I'd like to thank everyone for watching the presentation today. It's truly been a pleasure presenting to you. I'd also like to thank again the Canadian Agricultural Partnership for providing funding for this project, as well as our project partners, the Hydrogen Brethren and Alberta Agriculture and Forestry. I'd also like to thank all of you for supporting the Nutrient Management Seminar Series throughout its run. We greatly appreciate you registering for the event and watching all the presentations. The winners of the door prize draw will be contacted later this week. If you have any questions, please contact me at bcalder@warnercounty.ca. Thank you again for registering for the series and watching the presentations. We hope you enjoyed the series.